You are told there is a hole in the universe, a region so underpopulated that for hundreds of millions of years, light can cross it and almost never hit a galaxy. And then you are told it is not actually empty. That is the basic shock of the Boötes void. This thing is roughly spherical, around 330 million light years across. In metric, that is about 3.1 times 10 to the power of 21 kilometers. In miles, around 1.9 times 10 to the power of 21. If you take the average density of galaxies in the nearby universe and you apply it to that volume, you expect something like 2,000 reasonably bright galaxies. Instead, with real observations, you get only about 60, and later work shows that a lot of those 60 sit along a kind of tube through the middle rather than filling the space. A place that was supposed to be a clean hole turns out to have a hidden structure inside it. But before we continue, please subscribe to the channel to give your support. Let's continue. Before you can really feel how strange that is, you need a clear idea of what void means in cosmology, because it does not mean absolute nothing. The universe, on large scales, is full of structure. You have dense clusters of galaxies, long filaments, wide walls, and in between, lower density regions. When cosmologists say cosmic void, they mean a region where the number of galaxies per unit volume is much lower than the cosmic average, typically less than about 10% of that average. So if the average gives you one galaxy in some box of space, a classic void might give you one galaxy in 10 boxes of the same size. In the Boötes void, this drop is even more extreme. Compared to what you would expect for its size, the galaxy count is down by roughly a factor of 30. That is not a minor dip. That is a serious underdensity, a deep low point in the large-scale pattern of matter. The problem is, your intuition was not built for these scales, so it helps to anchor it. Start with the Milky Way. Your galaxy is about 100,000 light years across from one side of the disk to the other. A light year is the distance light travels in 1 year, moving at 300,000 kilometers per second, about 186,000 miles per second. Those numbers alone already feel huge. Now put the Milky Way into the Boötes void as a ruler. To go from one end of the void to the other, you could lay more than 3,000 Milky Way-sized disks in a straight line. Not 3 or 10, but over 3,000 huge galaxies, end to end, across a region that still has almost no bright galaxies compared to what you expect. You can also look at it as a time problem, which hits your intuition in a different way. Light is the speed limit of the universe. At 300,000 kilometers a second, it could go around Earth 7 times in 1 second. From the Sun to Earth, it takes a bit more than 8 minutes. Across the Boötes void, it takes about 330 million years. Roll back Earth's history by that much, and complex life is only just starting to really diversify. Dinosaurs do not exist yet. Humans are not even a concept. If you launched a photon from one side of this underdense region when early land plants were getting started, that photon would only now be reaching the far side. That is the timescale tied to this one structure that was sold as 1,000,000 cubic megaparsecs of nothing. So how did anyone get to the point of calling it 1,000,000 cubic megaparsecs of nothing in the first place? That phrase comes from the way astronomers describe volumes on cosmic scales. Instead of kilometers, they use parsecs. 1 parsec is about 3.26 light years. A megaparsec is 1,000,000 parsecs, so roughly 3.26 million light years. When they first mapped the Boötes region in 3 dimensions, they inferred that the void's volume was on the order of 100,000 to 1,000,000 cubic megaparsecs. That is a block of space so big that our usual human comparisons just fail. If you tried to fill that volume with Milky Way-sized dark matter halos, you could fit tens of millions of them. And yet, the early redshift surveys saw almost none of the luminous galaxies you would expect to sit in those halos. On those first plots, it genuinely looked like a huge cube of space had been carved out and left almost blank. At this point, a natural question is, could this just be a measurement issue? Maybe the telescopes were not sensitive enough. Maybe dust was blocking the view. Maybe the selection of target galaxies was biased in some subtle way. Those are always the first checks in astronomy. So observers went back. They pushed deeper, they used better instruments and different wavelength ranges, and they remapped that part of the sky. The result was not, oh, never mind, it's actually full. The result was, yes, there are galaxies in there, but nothing like the number you would expect. You get around 60 reasonably bright systems in that huge region, depending on where exactly you draw the boundary and how faint you allow your sample to go. That raw count by itself is already a strong statement. Out of a region where the simple statistics say 2,000 galaxies, you get only a few percent of that. But the spatial distribution of those 60 makes it even more interesting. You might think that if a region is underdense, whatever galaxies do exist inside it would be scattered more or less randomly. Instead, many of these Boötes void galaxies appear to lie along a tube-like structure cutting through the middle of the much larger low-density bubble. The hole in the universe is not featureless. It has a skeleton. So now the story is, there is a gigantic underdense region, about 330 million light-years wide, with a volume of up to 1 million megaparsecs, where the galaxy density is down by a factor of about 30. And inside that region, there is a narrow tube of galaxies, around 60 of them, running through the middle. Your earlier mental picture, a pure empty gap, is wrong. The universe did not simply leave a void. It left a weakened, thinned-out piece of the cosmic web in the middle of an extreme low-density bubble. That leads to the next question, and it's the one that turns a weird map feature into a serious cosmology test. How do you even find something like this in the first place, and how confident can you be that it's real, and not just an accident of how we sampled the sky? The answer starts not with a dramatic picture, but with narrow, careful measurements of galaxy redshifts in very thin beams of sky, and with a simple plot that suddenly showed a huge gap where galaxies should have been. How do you find one of the biggest deserts in the universe by looking at just a few thin lines on the sky? In 1981, Robert Kirshner and his team set out to do something simple and systematic. You pick a very narrow patch of sky, basically a skinny beam, you collect galaxies in that beam, and for each one you measure its redshift, its recession speed. From that, you reconstruct a three-dimensional slice of the cosmos along that line. This is called a pencil beam redshift survey. If the universe is statistically smooth on large scales, you expect those galaxy distances to be spread out in a fairly regular way. Some clumps, some gaps, but nothing absurd. Instead, in three different directions on the sky, the data came back with the same disturbing pattern, a huge gap in galaxy redshifts around the recession speed of roughly 15,000 kilometers per second. That speed is not just a random number. In cosmology, recession speed is how fast a galaxy appears to be moving away from you because space itself is expanding. The bigger the distance, the higher the speed. So when you look at a histogram of redshifts, you are really looking at how many galaxies you have at each distance along that narrow line of sight. In each of those three pencil beams, there was a clear drop, a real hole around that 15,000 kilometers per second mark. You're scanning along, seeing galaxies at lower speeds, more at higher speeds, and then suddenly there's a broad gap where the counts fall almost to zero. When you see that once, you can shrug. When you see it in three independent directions at roughly the same speeds, you have a problem you cannot ignore. So what does 15,000 kilometers per second mean in terms of distance? To turn that speed into a distance, astronomers use a simple relation between recession speed and distance built into the expansion of the universe. It says the farther away a galaxy is, the faster it appears to recede, in a roughly linear way, with a proportionality constant called the Hubble constant. Take a typical modern value, around 70 kilometers per second per megaparsec. If you divide 15,000 kilometers per second by that number, you get a distance of about 215 megaparsecs. 1 megaparsec is about 3.26 million light years, so you're sitting at a distance of roughly 700 million light years. In miles, that's on the order of 4.5 quintillion miles. You're literally using the expansion of space as a measuring tape. The speed tells you how far out the gap really is. To get a feel for the speed itself, 15,000 kilometers per second is about 33 million miles per hour. That's not just fast compared to a rocket, that's a significant fraction of the speed of light. And yet, in these surveys at that range of speeds, the galaxy counts just dropped off. When Kirshner's group followed up with more detail, they selected about 240 bright galaxies in those three beams and checked their redshifts carefully. Between around 12,000 and 19,000 kilometers per second, where a simple, uniform distribution would have put roughly 31 galaxies, they found none. Zero. That's not a small statistical fluctuation. That's a redshift hole, a range of distances where the beams run through space and barely touch any galaxies. At this point, you have to ask, is this just bad luck, or is it telling you something real about the structure of the universe? Three beams is not the whole sky. Maybe you just hit three weird directions. Maybe there's some observational bias. Maybe the selection of bright galaxies accidentally avoided a patch of interest. But when you run the numbers, the odds of getting that deep a gap in all three directions at similar ranges of recession speed, purely by chance, are low. That's exactly the kind of pattern that forces cosmologists to get serious and check with more data, more telescopes, and different methods. Later surveys did exactly that. They expanded beyond those narrow pencil beams, covering wider patches of sky, and they added many more galaxies with measured redshifts. Instead of looking at just three lines, you start to fill out a full three-dimensional region around that same distance, around 700 million light-years away. The pattern that emerges is not a thin tunnel of missing galaxies, but a large, roughly spherical underdense zone, a real void. The scale that falls out of those later measurements is a radius of about 62 megaparsecs, which is around 200 million light-years. That's just a radius. The full diameter is more like 100 megaparsecs, about 330 million light-years. And within that radius, the density of galaxies is way down compared to surrounding space. So you're not just missing a handful of galaxies that in principle could be explained by some small-scale fluctuation. You're missing an entire chunk of the cosmic web over a region hundreds of millions of light-years wide. In the surrounding volume, filaments, walls, and clusters make up the large-scale pattern of matter. Inside this range of distances, in this direction on the sky, that pattern collapses into a near void. When you correct for selection effects, for survey limits, and for the ways the data are collected, the underdensity remains. This is where the Boötes void starts to look like a genuine structural feature, not an observational accident. The really striking part is how all of this starts. There's no dramatic picture at the beginning, no high-resolution map. It starts with a simple bar chart, a histogram of galaxy redshifts in a pencil beam. You bin the galaxies by their recession speed, you count how many you have in each bin, and you plot the result. It should look noisy but continuous. Instead, you see something that looks like a canyon carved out of the distribution, a wide gap where the bars that represent galaxy counts drop down and stay down over a huge velocity range. From that gap, you infer a missing population of galaxies. From the missing galaxies, you infer a real three-dimensional underdensity. And from that underdensity, you eventually define one of the largest known cosmic voids in the observable universe. So you go from a line on a plot to a hole in the map of large-scale structure, and then to a named feature, the Boötes void, with a radius of about 62 megaparsecs and a diameter of about 100 megaparsecs, all because a few narrow surveys showed a gap that was too deep and too wide to ignore. And that brings up the next question, which should bother you if you care about how the universe is supposed to look on average. If this is the pattern you get from the real universe, what should an expected universe look like? How many galaxies should there be in a volume this large if everything followed the average rules? And how far does Boötes void actually deviate from that expectation? In a universe that likes to spread galaxies everywhere, how empty does a place have to be before you call it a cosmic desert, not just a quiet neighborhood? To answer that, you need a baseline, a picture of what normal looks like on large scales. In the nearby universe, if you take typical regions of the cosmic web, not inside a deep void and not inside a massive cluster, a rough back-of-the-envelope estimate gives you around one reasonably bright galaxy every 10 million light-years or so. 10 million light-years is already a huge gap, roughly 94 quadrillion kilometers, about 59 quadrillion miles, between one big galaxy and the next, and that is what normal looks like. Now scale that up to the size of the Boötes void. You are dealing with a span of around 330 million light-years across. If you step that out in units of 10 million light-years, you get on the order of a few dozen steps across in any direction, and when you turn that into a three-dimensional volume, that translates into something like 2,000 luminous galaxies you would expect if this region behaved like ordinary cosmic real estate. That is your first key number. Not 10, not 100, but roughly 2,000 galaxies as the default setting for a volume this big, if you are not sitting in an extreme underdensity. So then you ask, even if it is a void, how empty does it get? When astronomers map large regions of the sky with huge surveys, like the Sloan Digital Sky Survey, they do not just look at a few beams, they get redshifts for hundreds of thousands and then millions of galaxies. Out of that, they build catalogs of voids. They measure how many galaxies sit inside each low-density bubble, how big those bubbles are, and how deep the underdensities go. The result is pretty consistent. Typical voids tend to have galaxy densities that are about 10 to 20% of the cosmic mean. That means, even in a normal void, you still get 1/10 to 1/5 of the usual galaxy count. Apply that to a Boötes-sized volume, and you would still expect hundreds of galaxies, maybe 200, maybe 400, depending on the exact numbers. That is still a lot of galaxies. A void, in the usual sense, is not pitch black, it's just thinner. This is where Boötes void starts to stand out. Instead of a few hundred galaxies, you are seeing about 60 reasonably bright ones in the mapped volume. That's not 10% of the expected count, that's only a few percent. The density is not just low, it's pushed down to the extreme tail of what these surveys tend to find. When cosmologists talk about underdensity, they are not being poetic. They literally compute the galaxy number density as a function of radius inside a void. They take the center, they measure how many galaxies per cubic megaparsec you have there, they compare it to the field value outside the void, and they track how that density changes as you move from the core to the edge. For a typical void, that profile looks like this. In words, near the center, the galaxy density might be only around 10% of the value you get in normal regions. As you move out to about half the void radius, it stays low, then as you approach the edge, it climbs back up, and sometimes even overshoots, because matter has been pushed into a sort of shell around the empty zone. So you get a low, flat core, then a rising edge, then a return to roughly normal. That is the standard picture from both observations and simulations. In Boötes void, the underdensity remains extreme over a very large radius. You are not looking at a small, sharp dip, you are looking at a long, wide plateau of missing galaxies, spread across tens of megaparsecs. So you might think, maybe our theories never expected more galaxies there in the first place. Maybe this is fine. That is where the standard cosmology model, the one with dark energy and cold dark matter, comes in. In that model, voids are expected. When you simulate the growth of structure from small initial fluctuations, the underdense regions expand, matter flows out toward denser areas, and you naturally get bubbles of low density. But the simulations also show that even in these voids, you should still form plenty of small dark matter halos, which can host low-mass, faint dwarf galaxies. The big, bright galaxies are rare, but the little ones should be sprinkled through the void. Some theoretical estimates, based on these simulations, suggest that inside a Boötes-sized void, there could be thousands of very faint dwarf galaxies, well below the brightness limit of older surveys. These would have low luminosities, low surface brightness, and would be hard to pick out against the sky background, especially with older instruments and shorter exposure times. In metric, you might be looking at systems with stellar masses millions of times smaller than the Milky Way. In simple visual terms, they are tiny smudges of light instead of the obvious spiral disks you are used to seeing in pictures. This gives you a split picture. On the observational side, with the tools used so far, you detect about 60 reasonably bright galaxies inside the void. Given the sensitivity and depth of those surveys, that count is not crazy. It roughly matches how many luminous systems you can see when you point your telescopes in that direction and integrate long enough. On the theoretical side, if the standard model is correct, those 60 are only the visible tip, the easy part. Underneath, there should be a much larger hidden population of ultra-faint dwarf galaxies we simply don't see yet. In other words, the void is underpopulated, but probably not as utterly empty as it looks in our current catalogs. So how do you interpret the number 60 in that context? It's shocking in one sense, because compared to the 2,000 galaxies you would expect in a typical region of that size, and the few hundred you would expect in a standard void, it's incredibly low. It's a tiny fraction of the normal galaxy count. But it's not completely out of line once you factor in survey limits, detection thresholds, and the fact that faint dwarfs are hard to find. The observation is harsh on your intuition, but not fatal to the theory. It tells you that you are hitting the practical limits of your instruments and that the Boötes void is an extreme data point, but not impossible. However, there is still a detail here that theory doesn't set up for you automatically, and that is where the tension ramps up again. If you have an underdense region where galaxies are rare, you would normally expect the few that do exist to be more or less scattered through the volume. Random, sparse, but spread out. In Boötes void, that is not what you see. Many of those 60 galaxies seem to lie along a narrow tube-like structure cutting through the middle of the void. So you are not just asking why so few, now you have to ask why are the few that survive lined up in a tube instead of filling the space? Why do the few galaxies that live in one of the emptiest regions of the universe decide to stand in a line instead of using all the space they have? In the Boötes void, those roughly 60 detected galaxies are not spread out evenly through the volume. When you plot their three-dimensional positions, many of them sit along a tube-like structure running through the center of the void. Based on simple reasoning, you would expect the survivors in such an underdense region to be scattered more or less randomly. The volume is huge, the number of galaxies is small, so they should be smeared out. Instead, they are clumped into something that looks like a narrow corridor through a mostly empty room. That geometry is the first clue that you are not just dealing with a simple, uniform, low-density region. To understand why that tube is not just a curiosity, you have to step back and look at how galaxies arrange themselves on the largest scales. When astronomers map millions of galaxies in 3 dimensions, what appears is not a random cloud of points, but a pattern people call the cosmic web. You see long, thin structures called filaments, made mostly of dark matter with gas and galaxies tracing along them. Between those filaments, you have walls and clusters where several filaments meet, and in between all of that, you have the voids, the regions where there are very few galaxies. So even before you talk about the Boötes void, you already know the universe prefers lines and sheets, not uniform spread. Now, in numerical simulations of structure formation, when you start from small random density fluctuations and let gravity act for billions of years, something interesting happens to voids. Small voids can merge to form larger ones. Matter flows out of the underdense regions into the surrounding filaments and walls. As that happens, the big void is basically the result of several smaller, neighboring voids that have combined. But when you track the filaments in those simulations, you do not always erase them completely. Sometimes parts of a filament survive, threading through the underdense region, weakened but not gone. You end up with a large, merged void crossed by a thin, low-density filament that is still able to host some galaxies. This is one of the leading ideas for the Boötes void. Instead of being a single, simple bubble that grew from one underdense patch, it may have formed from the coalescence of several smaller voids over cosmic time. As those smaller voids grew and pushed together, the matter in between, especially along certain filaments, was pulled and stretched but not entirely removed. The result today is a megavoid with a radius of about 62 megaparsecs, roughly 200 million light-years, and across that space runs one surviving filament. That filament is now underpopulated compared to normal filaments in the denser cosmic web, but it is still there. The tube of galaxies you see is effectively the leftover skeleton of the web that once filled that region with more structure. That view also explains why the galaxies in the tube are not just random dwarfs. Observations suggest that many of the relatively bright galaxies in that structure form an overdense string compared to the rest of the void interior. In plain language, inside the overall underdensity of the Boötes void, that thin tube is locally the busy place. Across the full void, the average density of luminous galaxies is only a few % of normal space. Along the filament, the density of these bright systems is higher than in the surrounding empty space, and you can even find signs of interactions and activity. So you have an overdense line embedded inside a severely underdense background. It's like looking at a narrow, built-up strip of development along a highway, while the surrounding land, in all directions, is mostly unused. The contrast matters because it tells you the void is not featureless. It has internal structure that traces earlier stages of the web. This tube does not just matter for local bookkeeping. It's a test of how well your main cosmological model, the one with dark energy and cold dark matter, can reproduce the detailed geometry of the universe. The ΛCDM model does not just need to make voids with the right sizes and overall densities, it also has to produce the right patterns of filaments that pass through and around those voids. In high-resolution N-body simulations, you can ask a very direct question. If you create a universe with the same basic ingredients and let it run for billions of years, do you ever get a supervoid of roughly Boötes size crossed by a thin filament that hosts a small chain of relatively bright galaxies? If simulations frequently produce voids with no residual filaments, that would be a problem because the real universe clearly shows you at least one case where a filament survives. On the other hand, if simulations regularly produce merged supervoids with surviving internal filaments, then the tube and Boötes void fits naturally into that picture. At present, large cosmological simulations do show a network of voids and filaments that, in a statistical sense, matches what big surveys see. You do get cases where merged voids keep thin threads of structure inside them. That means the existence of the Boötes tube does not break ЛCDM, but it still pushes the model to match a more detailed constraint, not just the overall void size distribution. There's another angle here. The galaxies in the tube give you a way to measure how much matter behaves inside and around extreme underdensities. By studying their motions, their star formation, and their gas content, you can probe how much dark matter there is along that line compared to the surrounding void. You can also see how easily gas flows along the filament, how isolated those galaxies really are, and whether they show the same statistical trends as other void galaxies, such as being bluer and gas-rich. If that tube behaves like a standard filament dropped into a very low-density environment, it supports the idea that the cosmic web structure is robust even inside supervoids. If it behaves in a strongly different way, you might be looking at a sign that something about structure formation in extreme underdensities is still missing from your models. So you have turned what sounds like a small geometric detail, the galaxies form a tube, into a full diagnostic tool. The line of galaxies through the Boötes void is a visible trace of how voids merge, how filaments survive, and how galaxies occupy dark matter structures in extreme conditions. It's one of the specific patterns that any serious cosmological simulation has to be able to reproduce. If you can get the large void right, but you never see this kind of internal filament, that's a warning sign that your model is incomplete. Right now, the standard picture survives that test, but the Boötes void tightens the screws. With that, the next natural step is to stop treating those galaxies as anonymous points on a map and actually look at what they are. If these systems live inside one of the lowest density regions we know, and many of them sit along this surviving filament, what do they look like up close? Are they weak, fading remnants, or are they surprisingly active, still forming stars and feeding their central black holes in a place that, by large-scale standards, is almost empty? What does a galaxy look like when its nearest real neighbors are tens of millions of light years away in every direction? You might expect small, dim, tired systems, barely holding together in the middle of the Boötes void. When you actually zoom in, that picture falls apart. The galaxies that have been studied in and around this void are often surprisingly bright. In technical terms, many of them have absolute blue magnitudes brighter than -21, which puts them in the same league as large spirals in normal environments. On top of that, their spectra, the way their light is spread out by wavelength, often shows strong emission lines. So instead of quiet, passive galaxies fading in the dark, you are looking at systems that are turned up, not down. Those emission lines are a big clue. In optical spectra, sharp emission features usually mean one of two things, and often both. Either you have a lot of hot young stars pumping energy into the gas, or you have an active nucleus in the center, where gas is falling onto a supermassive black hole and heating up. In several Boötes void galaxies, the line strengths and ratios look like classic starburst regions or Cipher-type active galactic nuclei. A starburst is basically a phase where a galaxy's star formation rate shoots up, turning large amounts of gas into new stars in a relatively short time. Cipher galaxies are those where the central black hole is actively accreting, lighting up the core. So even in one of the lowest density regions you know, you are not seeing dead galaxies. You see systems in full on mode, forming stars, feeding black holes, and driving energetic processes that show up clearly in their spectra. That is the opposite of the naive expectation that a void should be full of weak, barely active leftovers. It tells you that the internal physics of a galaxy, plus a supply of gas, can keep things going even when the outside environment is extremely quiet. That raises a natural question. How do these galaxies still have enough fuel to run bright star formation and active nuclei if they live in such an isolated region? The key is that void galaxies, in general, tend to be gas-rich. Surveys of galaxies in low-density environments show high fractions of neutral hydrogen, the form of gas we call Hi. Neutral hydrogen emits at a radial wavelength of 21 centimeters, which makes it fairly straightforward to map with radio telescopes. When you do that for void galaxies, you often find large extended Hi disks, holding a lot of mass and cold gas. This gas richness makes sense when you think about what they're not experiencing. In dense clusters, galaxies slam past each other, merge, and get stripped by hot intercluster gas. Those processes remove gas and shut down star formation faster. In a void, those violent interactions are rare. The galaxies are so far apart that direct collisions are uncommon, and there is no massive hot atmosphere to blow gas out of their disks, so they can hold on to their fuel for a very long time. Their star formation does not have to be intense all the time, but it can be sustained, and occasionally, local conditions can trigger stronger bursts. Inside the Boötes void, you have concrete examples of this. One well-studied system is a galaxy called CG910. This object lives in what is supposed to be the middle of nowhere, yet it hosts a massive disk of molecular gas, the colder, denser form of gas that directly feeds star formation. Estimates put the mass of molecular hydrogen in CG910 at about 1.2 times 10 to the power of 10 solar masses. In plain language, that's around 12 billion times the mass of the Sun, just in cold molecular gas. The disk itself extends to about 7 kiloparsecs in radius, which is roughly 23,000 light-years across. That's about 13 times the radius of the Sun's orbit around the center of the Milky Way. This disk is not just sitting there, it's rotating at around 256 kilometers per second, which is about 570,000 miles per hour. That means the galaxy has a substantial gravitational potential, a serious dark matter halo, and a dynamically cold, ordered gas structure. When you see a flat rotation curve at that speed out to several kiloparsecs, you're looking at a well-developed galaxy, not a fragile borderline object. CG910 is a cold gas engine planted inside one of the most underdense regions we have mapped. So step back and look at the pattern. The void galaxies you can study in detail are not failing at being galaxies. They're doing the same basic things as galaxies in more crowded regions, just with different external conditions. Many are blue, which means their light is dominated by younger, hotter stars. Many are still forming stars at noticeable rates. They hold large reservoirs of gas, both neutral hydrogen and molecular hydrogen. Some host active nuclei. Their isolation has not stopped them, it simply reduced the number of interactions and sped down the clock for certain processes. This is why it's wrong to think of void galaxies as failed galaxies that never really got going. The evidence points the other way. The residents of the Boötes void are fully functional systems that just happen to live in a low-density environment. The environment did not switch off galaxy formation. It lowered the average density of galaxies and stretched out the timescales. With less external disturbance, secular processes, the slow internal evolution driven by gas inflow, disk instabilities, and gradual star formation, have more room to operate. That view has a direct consequence for how you read the Boötes void as a whole. You can't just dismiss it as a kind of cosmic error where structure formation missed a region and left it empty. The void contains real galaxies that are active and complex. It also probably contains many smaller, fainter systems that we haven't yet detected. The structure is not a perfect whole, it's a volume where all the same physical rules are playing out, just at a much lower galaxy number density. Once you accept those numbers as real, one more tension pops up. If the void is this big and this deep, and it sits this close in cosmic terms, why did it take so long to find more than a few dozen galaxies inside it? And how do astronomers actually track down a sparse population when almost every method is biased towards brighter, denser regions? How do you actually pin down a few dozen galaxies in a volume that big when all of your tools are built to find bright stuff in crowded parts of the sky? Once astronomers realized there was a serious underdensity in the direction of Boötes, the next step was not magic software or huge digital surveys. It started with something much more basic and honestly tedious. You have photographic plates from wide-field surveys, you look at them by eye, and you mark tiny smudges that might be galaxies. Then you go to a telescope with a spectrograph, you put those candidates on the slit, and you measure their redshifts one by one. Early follow-ups in the Boötes region did exactly that for a couple of hundred candidates. You're basically doing manual triage on faint blobs, deciding which ones are foreground, which ones are background, and which ones actually sit in that 700 million light-year distance range that defines the void. That method is slow and biased. You mostly pick galaxies that are big or bright enough to stand out on the plates. Low surface brightness dwarfs, which might make up a huge fraction of the true population, are easy to miss. But even with that limitation, this work started to fill in the picture. A small subset of those candidates turned out to have the right redshifts to live inside the Boötes void. That is where the around 60 luminous galaxies comes from. They are the ones you can reasonably detect with that kind of optical follow-up out to distances of hundreds of millions of light years. The next big stop came from changing the wavelength you look at. Optical plates and CCDs are great for starlight, but not for dust. Dust in galaxies absorbs optical and ultraviolet light and re-radiates that energy in the infrared. So if you want to catch dusty, star-forming galaxies that might not stand out in optical surveys, you go to the infrared. Missions like IRAS, the Infrared Astronomical Satellite, scan the sky at infrared wavelengths and produce catalogs of bright infrared sources. When astronomers cross-matched the Boötes void region with IRAS data, they found a set of infrared bright galaxies sitting inside the void's edges. One early deep survey in that direction picked up 12 IRAS galaxies associated with the void, and 7 of those were newly identified within the original void boundaries. These are dusty star-forming systems that might have been undercounted in pure optical searches. In simple terms, you are catching hidden galaxies by their heat, not their starlight. Even in a region where the overall number density is way down, some galaxies are converting gas into stars fast enough and with enough dust that they glow strongly in the infrared and show up clearly in these surveys. But dust and stars are only half the story. If void galaxies are gas-rich, you also want a direct tracer of that gas. Neutral hydrogen, the most common form of gas in galaxies, emits at a radio wavelength of 21 centimeters. HI surveys use radio telescopes tuned to that line to scan large regions of the sky. In and around the Boötes void, these surveys have turned up additional gas-rich galaxies, including systems where the neutral hydrogen disk stretches far beyond the visible stellar disk. That tells you two important things at once. First, some galaxies that live in or near the void are even larger in gas extent than they look in optical images. Second, you can miss them completely in optical catalogs if their stars are faint or spread out, while the gas still produces a strong radio signal. This is why multi-wavelength work matters so much. Optical, infrared, and radio surveys each see different pieces of the same population. When you combine them, you get a fuller census of who actually lives inside the void. And once you have that census, you can start to ask not just how many, but what kind. Recent work goes beyond just flagging galaxies as in the void and starts classifying their internal physics. One common tool is to use emission line ratios in their optical spectra to separate star-forming galaxies, composite systems, and active galactic nuclei. Star-forming galaxies have line ratios dominated by young, massive stars. AGN show line ratios shaped by harder radiation from the accretion disk around the black hole. Composite systems sit in between. Apply that to Boötes void and you find a spread. Some galaxies are clearly star-forming, with strong hydrogen and oxygen emission lines. Some show composite signatures, suggesting both star formation and a weakly active nucleus. Some look like classic Seyfert-type AGN, where the central black hole is accreting and lighting up the core. So you don't have a single flavor of galaxy in the void. You have a mix of normal star-forming disks, dusty infrared bright systems, gas-rich HI galaxies, and active nuclei. The environment is extreme, but the types of galaxies are familiar. Given all this effort, you might reasonably ask why people still talk about 60 void galaxies, instead of quoting a precise number. The reason is that the count depends sensitively on technical choices. First, where exactly do you draw the boundary of the Boötes void? Different authors use slightly different radius estimates or slightly different center positions based on updated redshift surveys. Shift the boundary a bit and a few galaxies move in or out of the defined volume. Second, what brightness limit do you use? If you only count galaxies brighter than a certain absolute magnitude, you get one number. If you push a bit fainter, you pick up more systems. Early work focused on relatively bright galaxies because that's what the instruments could see efficiently at those distances. As newer surveys go deeper, detecting lower luminosity galaxies and lower surface brightness systems, the catalogs inside the void slowly grow. Third, survey depth and completeness are not uniform across all wavelengths and all parts of the sky. Some regions of the void have better coverage in radio, some have better infrared mapping, some have deeper optical spectroscopy. So one team combining optical and IR data might quote one count, while another team adding extra HI detections might quote a slightly higher number. When you gather these together, you land in the range of 50 to a bit over 60 known galaxies inside the main volume. The crucial point is that whatever the exact current count is, 50, 60, or 70, it's still tiny compared to the roughly 2,000 you would expect in a normal region of that size, and still tiny compared to the few hundred you might expect in a typical void of similar volume. Even as newer surveys slowly add more faint dwarfs to the list, the Boötes void remains a cosmic ghost town by any reasonable standard. It's underpopulated by an order of magnitude or more, and that makes it a natural stress test for your models. Which brings you to the next sharper question. If you have a 330 million light-year wide underdensity with only a few bright galaxies and probably a hidden cloud of faint dwarfs, does that push the standard cosmological model past its breaking point? Or does it actually end up confirming that the universe, even at its most extreme, still fits inside the current rules? Is a 330 million light-year hole in the galaxy distribution actually allowed by our main model of the universe? Or is it a sign that something is broken? That is the first thing people asked when the Boötes void was nailed down. You have a region hundreds of millions of light-years wide, with galaxy density down by roughly a factor of 30, and a weird tomb of galaxies running through it. At a glance, it feels too big, too smooth, too extreme. Early on, some discussions treated it almost like a potential glitch in ΛCDM, the standard model that combines dark energy, cold dark matter, and ordinary matter into one framework. If your main theory cannot produce something like the Boötes void, that is not a small issue. That is a red flag. To see how serious that worry is, you need a quick, plain language picture of what ΛCDM actually says. In that model, most of the mass in the universe is dark matter, which interacts mainly through gravity and moves slowly compared to light, hence cold. On top of that, you have dark energy, which acts like a kind of uniform energy density driving the accelerated expansion of the universe. Ordinary matter, the stuff that forms atoms, stars, and you, is only a small fraction of the total. At early times, the universe is almost uniform, with tiny density ripples seeded by quantum fluctuations. As time goes on, gravity makes the slightly denser regions collapse into filaments, walls, and clusters, and the slightly underdense regions expand into voids. The obvious test is simple. If you start with those initial conditions and evolve them forward in a simulation that follows billions of dark matter particles, do you ever see voids as large and as deep as the Boötes void? Big N-body simulations do exactly this. They take a huge volume, sometimes hundreds or even thousands of megaparsecs across, populate it with dark matter particles, and let gravity evolve the system for billions of years, while the overall expansion follows the ΛCDM rules. When you analyze the outputs, you find a network of filaments and voids that look statistically similar to what big surveys like the Sloan Digital Sky Survey see. In those simulations, you do get big voids, and you even get supervoids when smaller voids merge. If you measure their sizes and how many of them you get at each size and compare that distribution to real data, the match is surprisingly good. The number density profiles, meaning how the density changes from the center of a void out to its edge, also line up. Most voids have flat, low-density centers and rising edges, just like the observed ones. The Boötes void sits near the extreme tail of that size distribution, but not outside it. In other words, ΛCDM does produce objects that look like Boötes-scale voids. They are rare, but they are not forbidden. That takes the edge off the too big worry, but it does not end the story, because you also need to check the galaxies themselves, not just the dark matter skeleton. Galaxy formation models built on top of ΛCDM simulations predict that galaxies and voids should not look exactly like galaxies in crowded clusters or average density regions. They should, on average, be bluer in color, which means they have a higher fraction of young stars. They should be more gas-rich, with larger HI reservoirs. They should show higher specific star formation rates, meaning more star formation per unit stellar mass, because they have kept their gas and avoided the harsh stripping processes common in clusters. When observers look at samples of void galaxies, including those in and around the Boötes void, that is roughly what they see. The typical void galaxy is more likely to be a blue, star-forming disk with lots of neutral hydrogen and ongoing star formation than a red, quenched elliptical. Even inside the Boötes void, you find luminous, blue systems with active star formation, and in some cases, active nuclei. That's exactly the direction the models point. So on the galaxy properties versus environment test, ΛCDM plus standard galaxy formation physics does not fail. The void galaxies are behaving the way the theory expects galaxies in low-density regions to behave. The real tension shows up when you stop looking at the big, bright systems and start asking about the smallest galaxies, the faint dwarfs. In ΛCDM, dark matter halos form on a wide range of mass scales, and there should be many more small halos than big ones. That's true in clusters and in voids. The small halos and voids hold less mass, but there should still be a lot of them. If galaxy formation is efficient enough in those halos, you should end up with a large population of low-mass, low-luminosity dwarf galaxies scattered through the void. They might be faint and hard to detect, but if you add up the predicted halos, there should be thousands of potential hosts inside a Boötes-sized void. Right now, the number of actually observed faint dwarfs and deep voids is nowhere near that. To be fair, they are extremely hard to see. At distances of hundreds of millions of light years, a dwarf galaxy with a very low surface brightness is almost invisible against the sky background. It can be missed by automatic source detection algorithms and even by careful visual checks. That's why people are cautious. They know there's a strong observational bias against exactly the population that would test the theory the hardest. This sets up a clear, high-stakes situation for future surveys. If upcoming ultra-deep, high-resolution imaging projects, which will push much further down in both luminosity and surface brightness, eventually find a large population of faint dwarfs and voids like Boötes, then the small-scale structure predicted by ΛCDM gets a major boost. The missing halos aren't missing. Their galaxies were just too faint to see before. On the other hand, if those surveys keep improving and still don't find nearly enough dwarf galaxies inside voids, then you have a real stress test for how galaxies populate dark matter halos. Either something about feedback and star formation in small halos is drastically different than what we think, or, in the more radical case, the underlying dark matter picture might need adjustment. So where does that leave the Boötes void right now? On large scales, its existence, its size, and its basic density profile are consistent with ΛCDM simulations. On the galaxy property side, the bright void galaxies behave in line with expectations. They are blue, gas-rich, and actively forming stars. On the small-scale halo side, the situation is not yet fully tested because the observations are not deep enough to give you a definitive dwarf galaxy census. The tension is more of a warning sign than a fatal blow. The current consensus is pretty clear. The Boötes void is extreme, but not illegal. It's a statistical outlier in a ΛCDM universe, the kind of rare, large underdensity that you expect to see a handful of times across the observable volume. It just happens that one of those outliers is close enough and obvious enough for us to map and argue about. That actually makes it valuable. Instead of breaking the model outright, it gives you a sharp, focused tool to test the edges of that model. If ΛCDM can handle Boötes and other supervoids, it passes a tough exam. If it fails, it will probably fail here first. Once you accept that the big picture isn't broken, you can turn to a more subtle but equally important question. If the standard model survives, what does life, in the sense of galaxy evolution, look like in a place where the external environment is turned down so far? In a cluster, galaxies are battered by interactions, stripped of gas, and forced to evolve violently. In a void like the Boötes void, none of that is dominant. So how do galaxies change when almost nothing ever disturbs them? In a dense cluster, the story is chaos. Galaxies swing past each other, merge, shove gas around, and plow through hot intercluster gas that strips material out of their disks. Collisions and ram pressure dominate the script. In a void like the Boötes void, that script almost disappears. The distances between big galaxies are so large that close encounters are rare. There's no massive hot atmosphere to blow gas away, so the main drivers are internal, what astronomers call secular evolution. Gas slowly drifts inward through the disk, spiral arms and bars rearrange material, and stars form at a steady, moderate rate, not in huge cluster-triggered bursts. So what does that look like in hard numbers for a real void galaxy? Take CG 910 again, that gas-rich system sitting deep in the Boötes void. If you add up its gas content, both the cold molecular hydrogen that directly feeds star formation and the more extended neutral hydrogen, and compare it to the mass already locked up in stars, you get a gas-to-stellar mass ratio of roughly 70%. In other words, the galaxy still has gas mass that is about 7/10 of its stellar mass. At the same time, its current star formation rate is not extreme. Put those together and you get a long gas depletion timescale. At the present rate of turning gas into stars, it would take billions of years to use up the fuel. In a massive cluster, a similar galaxy might lose most of its gas in a relatively short time because of stripping and interactions. In the void, CG 910 can just keep going, slowly, for a large fraction of the remaining cosmic time. That immediately raises another question. If the environment is this gentle, do even the old-looking galaxies stay active longer? In many dense regions, early-type galaxies, the ones with smooth light profiles and big bulges, have already quenched. Their star formation has basically stopped, and they are dominated by old red stars. In the Boötes void, you still see early-type systems, but when you analyze them in detail, they do not always behave like fully quenched cluster ellipticals. For example, galaxies like IZ-181 show signs of central star formation and active nuclei. When astronomers decompose their light in two dimensions, separating the bulge from any disk or bar components, and then look at emission line diagnostics, they find evidence for both ongoing star formation near the center and AGN activity tied to a feeding central black hole. So you're looking at galaxies that, in a dense environment, might have been shut down by mergers, stripping, or feedback from earlier, stronger AGN phases. In the void, those same types can keep low-level activity running. The external events that would normally slam the brakes on star formation just don't happen as often. That's the theme. Less external violence, more extended, slow evolution driven by the galaxy's own gas and internal dynamics. Zoom out from individual case studies and look at the statistics. When you compare samples of void galaxies to galaxies in average density regions, you see clear trends. Void galaxies tend to be bluer. That means their light is weighted more toward young, hot stars, not dominated purely by old red populations. Morphologically, they often have lower bulge-to-disk ratios. In plain terms, less massive central bulges and more prominent disks. That's consistent with fewer major mergers, because big mergers tend to build up bulges and turn disks into more spheroidal systems. Why does that matter for the story of Boötes void? Because it tells you that the environment has not just lowered the number of galaxies, it's shifted the evolutionary pathways of the ones that remain. With fewer disruptive encounters, disks stay intact longer, gas reservoirs survive, and star formation histories stretch out over longer periods. Instead of compressing a lot of evolution into a few violent events, void galaxies spread their evolution over many billions of years, slowly changing color and structure while the universe around them thins out. This is where the idea of voids as natural laboratories comes in. The Boötes void is not just a blank region you skip over on a map. It's a controlled experiment set up by the universe itself. In a cluster, you can't easily separate what is driven by internal processes from what is driven by external hits, because everything is happening at once. In a void, the external hits are largely removed. You dial the background galaxy density way down, you stretch out the times between interactions, and you let gravity plus gas physics run with minimal interference. So when you study galaxies in the Boötes void, you're effectively watching a slow-motion version of galaxy evolution, where secular processes are easier to isolate. You see how long gas can last when it's not stripped. You see how disks evolve when they're not constantly shaken by mergers. You see how central black holes behave when fuel arrives gradually, not in big, merger-triggered dumps. The emptiest places turn into clean testbeds for the physics that also operates, but is harder to disentangle in the busier regions. Once you realize that, the next question is bigger than just what do void galaxies look like. You have to ask how the Boötes void fits into the full three-dimensional pattern of the cosmic web. It's not floating alone. It sits between walls and filaments that define the edges of the underdensity. So how does this huge hole connect to the surrounding superclusters and the network of filaments that stretch across hundreds of millions of light years? When you stop looking at single galaxies and actually plot millions of them in 3 dimensions, the universe stops looking like a random spray of points and starts looking like a structure with rules. Positions from big redshift surveys line up into long filaments, broad walls, and dense nodes where filaments cross. In between these, you see big, underdense bubbles, the voids. Put all of that together, and it looks like a foam of matter and emptiness on scales of hundreds of millions of light years. In that foam, the Boötes void stands out as one of the largest bubbles we've mapped, a huge low-density pocket carved out of the cosmic web. You can see that directly when you stack galaxy maps that extend over large chunks of the sky. Dense regions show up as thick chains and sheets of points. The empty regions show up as patches where the points thin out dramatically. The Boötes void is not some subtle dent. It's a clear low-density region sitting among strong walls. That's why it was noticed at all. If it were small or shallow, it would vanish into the general noise of the web. Instead, it opens up as a real gap between the main structures around it. Those surrounding structures aren't just generic background. They're superclusters, the largest bound collections of clusters and groups that we see. On one side of the Boötes void, you have the Hercules supercluster and the Corona Borealis supercluster, big concentrations of galaxies and dark matter. Around other parts of the void, you find the Boötes supercluster and additional massive structures. On the map, they form a rough shell of higher density regions, a ring of strong gravitational wells around the lower density interior. In practical terms, that means the Boötes void is not just empty space over there. It's the central underdensity between several very large overdensities. Gravity pulls matter into those walls and nodes over billions of years, and as that happens, the region in between loses matter and becomes emptier. You're literally watching how contrasts in the density fields sharpen with time. Dense regions get denser, empty regions get emptier. The edges of the Boötes void are where that process has gone farthest in this part of the universe. Now, look at how voids grow in simulations. Start with a universe that is almost uniform, with tiny over and under densities. As time passes, material flows. Slightly over-dense patches become filaments and clusters. Slightly under-dense patches expand more quickly than the background and push matter outward. At first, you have many small voids scattered between filaments. As structure grows, neighboring voids can merge. Their boundaries shift, their central regions combine, and what used to be several small bubbles becomes one larger bubble. The filaments between them get thinned out or partially erased. This process, repeated many times, naturally builds supervoids that are much larger than the initial underdense regions you started with. In that context, the Boötes void looks like a late product of this hierarchical merging. Several smaller voids likely combined, with surrounding matter drained into the bordering superclusters. The internal filament we see as the tube of galaxies is what remains of a denser region that did not completely disappear. So the shape and size of the void are not just random, they are the end result of billions of years of gravitational evolution operating on an initial pattern of density fluctuations. That initial pattern is where the deeper cosmology comes in. The large underdensity you call the Boötes void did not appear from nowhere halfway through cosmic history. It traces back to a region in the early universe that started slightly less dense than average. The properties of that initial region are set by the statistics of the primordial fluctuations, the tiny ripples in density that were imprinted shortly after the Big Bang, and then stretched by cosmic inflation. When you study a structure as extreme as the Boötes void, you are indirectly probing those initial conditions. If the primordial fluctuations are described by a certain power spectrum, which tells you how much structure exists on different length scales, then there is a specific probability for getting a fluctuation large enough and extended enough to grow into a Boötes-sized void. Measure enough voids, including their sizes, shapes, and depths, and you can constrain that power spectrum. Measure their distribution across the sky, and you can test whether the fluctuations are Gaussian in the sense that they follow a simple statistical pattern, or whether there are extra features that hint at more complex physics in the early universe. This is why embedding the Boötes void into the full cosmic web changes its role. If you look at it as a single whole, it is just a curiosity, a piece of trivia about a big empty region. When you place it in its real environment, bordered by specific superclusters and connected to real filaments, it becomes a data point in the network. Its size, its position relative to other structures, the fact that it hosts a surviving internal filament and a small set of active galaxies all feed into how you test your cosmological model against reality. On top of that, the Boötes void helps bridge scales. Inflation and primordial fluctuations operate on scales far beyond single galaxies. Star formation, gas dynamics, and black hole activity operate inside galaxies. A supervoid like Boötes sits between those extremes. It is large enough to be sensitive to the initial density field and detailed enough to contain galaxies whose properties you can measure. By connecting the behavior of those galaxies to the properties of the void and its place in the cosmic web, you are linking the smallest observable scales of galaxy physics to the largest scales of cosmology. So, the Boötes void is not just an empty patch you label and move on from. It is part of the scaffolding of the universe's structure story. It marks a region where early underdensities grew into a huge supervoid, while surrounding overdensities grew into superclusters. It shows that void merging and filament survival happen the way simulations predict, and it feeds back into the constraints on the initial fluctuations that inflation stretched to cosmic scales. Once you see it that way, another question becomes impossible to ignore. If the Boötes void is one of the largest and emptiest bubbles in this cosmic foam, how rare should a structure like this actually be? Are you looking at a once-in-a-Hubble volume anomaly, or the kind of extreme object you expect to see a handful of times in a universe this big? Put differently, does the sheer existence of a void this large sit comfortably inside the statistics of ЛCDM, or does it push you toward the edge of what the current model can justify? How close is the Boötes void to something the universe should not be able to make? To answer that, you have to look at how void sizes are actually distributed. When you build catalogs of voids from big surveys or from ЛCDM simulations, you do not get a flat spread of sizes. Small voids are common. As you go up in radius, they drop off fast. By the time you hit voids with radii above 30 or 40 megaparsecs, you're already in the rare category. The Boötes void, with a radius of about 62 megaparsecs, roughly 200 million light-years, sits way out on that tail. It's not just large, it's at the extreme end of the size distribution that both data and simulations agree on. A useful way to talk about that is the sigma language cosmologists use. Think of the early universe as having a nearly uniform density with small random fluctuations. Those fluctuations can be described statistically in terms of how far a region's density deviates from the mean. 1 sigma is a typical deviation. 2 sigma is rarer. 3 sigma is rarer still. A multi-sigma fluctuation is something that is definitely not average, but still allowed by the statistics. The Boötes void traces back to a region that in the early universe started a bit underdense. Over time, because underdense regions expand faster and matter drains into surrounding overdense zones, that small initial deficit grew into a dramatic underdensity. So you can think of the Boötes void as the evolved form of a multi-sigma underdensity in the primordial field. It's not a place where the laws of physics changed. It's a place where a low probability initial condition actually occurred in a large universe. Given enough volume, even low probability events show up somewhere. The key question is whether they show up as often as ЛCDM predicts, or more often or less often. This is where the concept of a Hubble volume comes in. You can roughly define the observable universe as a sphere centered on us, out to the distance light has had time to travel since the Big Bang, about 46 billion light-years in radius. The total volume of that sphere is enormous. If you run ЛCDM simulations over a similar effective volume, you can ask a concrete question. In a universe this big, with these initial conditions, how many supervoids with Boötes size and depth do you expect? The answer is not 0 and not thousands, it's more like a handful. You expect a small number of really large, deep voids across the whole observable universe. The fact that we have identified at least one, the Boötes void, at around 700 million light-years is statistically lucky for us as observers, but not absurd in the context of the model. If we had found 10 or 20 Boötes-level voids within that same distance, that would have been a different story. One big one, plus a few other comparable structures further out, sits within the range ЛCDM can live with. And in fact, Boötes is not the only extreme underdensity people talk about. There's the so-called KBC void, a proposed large underdense region in the local universe that has been invoked in some papers to try to explain why local measurements of the Hubble constant seem higher than global ones. There are other cataloged supervoids with sizes of several hundred megaparsecs, identified in various surveys. The exact details for each of these are still under debate, but the point is that the Boötes void is part of a small family of very large and underdense regions, not a unique one-off. That gives you multiple data points when you compare observations to simulations. When you line up these extreme voids against LCDM predictions, the match is not perfect in every detail, but the counts are not wildly off either. You do not see an obvious shortage or obvious overabundance of supervoids, given the current uncertainties. That is important because rarity cuts both ways. If Boötes scale voids were much more common than simulations predict, that would signal a problem with the initial fluctuation spectrum or with how matter clusters over time. If they were far rarer than observed, or basically absent in simulations, that would also be a problem. Either way, you would be pushed to tweak dark energy, dark matter, or the way the early fluctuations are set up. Right now, the numbers line up just well enough to avoid that. The Boötes void is rare, but its rarity is roughly what you expect in a LCDM universe of this size. That keeps the standard model alive, but it does not give it a lot of slack. As surveys improve and more supervoids are cataloged with better statistics, the room for error shrinks. If the updated void counts start drifting away from the predicted distribution, the tension will grow. There is another subtle point here. Rarity by itself does not tell you the whole story. You also care about the internal details, the density profile, the presence or absence of internal filaments, the mix of galaxy types, and how the void lines up with other large-scale structures and with signals in the cosmic microwave background. A structure can be rare in size, but very standard in profile, or more common in size, but unusual in how sharply the density drops. The Boötes void earns attention because it is large, deep, and fairly clean, with a relatively simple internal geometry dominated by that one main filament. So you end up with a kind of narrow path for the model. The Boötes void has to be rare enough to sit on the tail of the distribution, but not so rare that simulations almost never produce it. It has to be extreme enough to test the model, but not so extreme that it breaks it. With current data, LCDM manages to walk that line. The Boötes void is almost impossible in the intuitive sense, but not impossible in the strict statistical sense. That still leaves a practical problem. To really lock this down, you can't just rely on one wavelength or one type of survey. You have to see the void and its galaxies across the spectrum: optical, infrared, radio, even millimeter. Each band picks up different pieces of the physics. Only when you stack those views together do you get a complete picture of how such an extreme underdensity actually works in detail. How do you actually prove that a place people call the Great Nothing is still busy once you stop staring only at visible light? Start with the simplest toolset: optical telescopes and spectrographs. In optical, you get three core pieces of information about Boötes void galaxies. First, redshifts, which tell you how fast they are receding and therefore how far away they are. That's how you confirm they really sit inside the void volume at around 700 million light-years instead of being foreground or background. Second, you get basic morphology from images: disks, spiral arms, bars, irregular clumps, smooth early type shapes. In the Boötes void, you do not just see one class. There are spirals, irregulars, and early type systems, sometimes with visible disks and sometimes more compact. Third, spectra give you emission and absorption lines that tell you what's going on physically: star formation, shocks, and active nuclei. Even on simple optical images, you're already seeing a mixed population, not some single void-only galaxy type. Once you put those spectra under a microscope, the picture gets more detailed. Strong hydrogen and oxygen emission lines show ongoing star formation. Line ratios flag whether the ionizing source is mainly young stars or a harder radiation field from an accreting black hole. In Boötes void, you pick up both behaviors. Some galaxies fall cleanly in the star-forming category, with line ratios typical of H2 regions. Others drift into the composite or AGN zones, consistent with ciphered-like nuclei. So at optical wavelengths alone, the void is not just a passive repository of old stars. It has active disks, bulges with central activity, and a spread of morphologies that looks familiar from denser environments, just sampled at much lower number density. The next question is what you miss when you look only in optical. Dust can hide both young stars and compact central activity by absorbing their light and re-emitting it at longer wavelengths. To pick that up, you go to the infrared. Infrared missions like IRIS and later observatories with better sensitivity and resolution scan the sky at wavelengths where dust glows strongly. When you cross-match those catalogs with the Boötes void region, you find dusty, infrared luminous galaxies inside a volume that, on the optical map, looks almost empty. One early deep look pulled out a dozen IRIS sources linked to the void, 7 of them newly recognized inside the original void boundaries. Those objects are not quietly fading systems. They are dusty starbursts and luminous infrared galaxies, which means large amounts of gas are collapsing into stars and heating dust grains, driving total infrared luminosities that can rival or exceed their visible output. So even in a region where the average galaxy density is down by a factor of tens, local pockets still hit intense star formation modes. Optical alone underestimates that because dust masks some of the most active regions. Infrared fills that gap by flagging the heat from dust as a tracer of hidden star formation. Then there's the fuel question. Starlight and dust emission tell you what is happening now. To see what could happen in the future, you need to measure the gas reservoirs. Neutral hydrogen, the most basic form of galactic gas, radiates at a radio wavelength of 21 centimeters. Point radio telescopes at the Boötes void and tune to the right redshifted frequency, and you can detect HI gas in galaxies that may look small or faint in optical images. Radio surveys in and around the void reveal extended gas disks, often stretching far beyond the visible stellar components. In some cases, the HI distribution is warped or asymmetric, signs that even in low-density environments, minor interactions or past accretion events have left an imprint. The kinematics from these HI maps, the way the gas is moving, show dynamically active systems. Rotation curves flatten at velocities of a couple of 100 kilometers per second, hundreds of thousands of miles per hour, consistent with substantial dark matter halos. Combined with large gas masses, this tells you these are not marginal, barely held together galaxies. They are stable, rotating systems with plenty of fuel left to tap, even though they live in a part of the universe where bright neighbors are rare. On top of the neutral gas, there is the denser molecular phase, the direct feedstock for new stars. To see that, astronomers go to millimeter wavelengths and observe emission from molecules like carbon monoxide. The CO1 to 0 line, in particular, is used as a tracer of molecular hydrogen, which is hard to detect directly. In CG910, the molecular mapping is detailed enough to resolve a disk. The measured rotation curve is flat out to about 7 kiloparsecs, roughly 23,000 light-years, at a speed of around 256 kilometers per second, about 570,000 miles per hour. From the CO line strength, you infer a molecular gas mass of roughly 10 billion solar masses. Put that in plain terms. CG910 has a cold molecular disk about 13 times the radius of the Sun's orbit around the Milky Way's center, spinning at a few hundred kilometers per second and holding around 10 billion times the mass of the Sun in star-forming gas. All of that is sitting inside a region that, at the large-scale level, you describe as almost empty. On a galaxy-by-galaxy basis, there is nothing weak about it. The units on the paper are all metric, kilometers per second, kiloparsecs, solar masses, but they translate to high speeds, big sizes, and large fuel reserves in everyday language. Once you bring all these bands together, the pattern is hard to ignore. Optical data prove the underdensity and give you morphology plus basic activity indicators. Infrared data reveal dusty starbursts and luminous IR galaxies that optical surveys partly miss. Millimeter HI imaging exposes extended gas disks, ongoing gas accretion, and dynamical structure beyond the visible light. Millimeter CO mapping shows dense molecular gas disks with substantial rotation and mass. Across the spectrum, you see complexity, motion, and active physics. So the combined multi-wavelength verdict is simple and sharp. The Boötes void is severely underdense in the number of galaxies. The volume is mostly empty when you count big, bright systems per cubic megaparsec. But the galaxies that are there are not ghosts. They are gas-rich, dynamically alive, and active across the spectrum. The emptier label applies to the statistical galaxy count, not to the internal physics of the residents. The emptier the large-scale environment gets, the clearer it becomes that even a small number of galaxies can host a full range of processes: star formation, black hole feeding, gas inflow, and secular evolution, all running in parallel. That raises a very direct next question that shifts the focus from pure cosmology towards something more personal. If you can have fully functional, star-forming, gas-rich galaxies stringing through a void like this, could a galaxy like the Milky Way and a planetary system like yours live in a place as underdense as the Boötes void without noticing anything obviously wrong in day-to-day life? Could you actually live inside a place like the Boötes void, and would you even notice anything strange just by looking up? On the level that really matters for habitability, the answer is basically no, you would not. Structure formation does not simply shut down in voids. If you drop a Milky Way-like galaxy into the Boötes void with a similar dark matter halo and gas content, it can still form stars, build planets, and generate the heavy elements you need for chemistry and life. The galaxies we actually see in the void already prove this. They have gas, they have ongoing star formation, and they show metal lines in their spectra, meaning previous generations of stars have already built heavier elements like carbon, oxygen, and iron. They are not starved of the basic ingredients. On that level, a void galaxy is real habitable real estate. So what would actually feel different for an observer living on a planet in one of those galaxies? Start with the night sky in the most direct sense, what you see with your own eyes. The local sky is dominated by your own galaxy. For us, that's the Milky Way band across the sky, star clouds, nebulae, and so on. In a void galaxy, you still have a galactic disk, tens of thousands of light years across, loaded with hundreds of billions of stars. That dominates your naked eye view either way. The difference shows up when you start looking beyond your own galaxy. From a void galaxy, the extragalactic backgrounds would be thinner. There would be fewer bright neighboring galaxies scattered across the sky, and fewer obvious rich clusters with tight knots of bright galaxies. With a decent amateur telescope, in our real universe, you can point at certain regions and see groups and clusters quite easily. In a deep void, similar equipment would show fewer such targets at the same brightness levels. Professional telescopes would still pick up background galaxies at great distances, because the void is a local underdensity, not a full hole in the universe. But the nearby bright companions would be rarer. You would see less busy surroundings in three-dimensional maps. The more serious differences show up when you go beyond direct images and start doing precision cosmology. Supervoids like Boötes can leave subtle imprints on the cosmic microwave background, the leftover radiation from the Big Bang. As photons from the CMB pass through a large, evolving underdensity, their energies are shifted slightly by the changing gravitational potential. This is known as the integrated Sachs-Wolf effect. The signature is tiny, a very small temperature variation across the CMB sky, but in principle, if you sit in or near a deep void, those line-of-sight effects can change the detailed pattern you measure. That means that for an advanced civilization doing precision measurements, the inferred values of certain cosmological parameters might shift slightly depending on where in the large-scale structure they are located. The basic story that the universe is expanding and that the CMB has a roughly uniform temperature of about 2.7 Kelvin doesn't change. But the fine details of how you fit large-scale structure, CMB anisotropies, and expansion history could look a little different if your vantage point is in a deep void versus in a more average region. The physics is the same, but the local environment adds a small bias to some of your measurements. That leads into the anthropic style question people like to raise, but here we can keep it concrete. Our local group, which includes the Milky Way and Andromeda, sits in a relatively typical environment, not inside a Boötes-level supervoid, not in the core of a coma-like massive cluster. It's somewhere in between. The open question is whether that's just a random draw or whether the emergence of technological observers is slightly more likely in these middling environments. Dense clusters may be too violent, with more frequent galaxy interactions, stronger radiation backgrounds, and faster quenching of star formation. Deep voids may evolve slowly, with fewer heavy mergers and fewer bright neighbors, but as we've seen, they still form perfectly normal galaxies with plenty of gas and metals. The Boötes void gives you one boundary condition on that problem. It shows that an extremely underdense region can still host galaxies that look completely viable for habitability in terms of stars, gas, and metals. It suggests that the main constraints on where life can appear are more local, tied to the specific galaxy and its internal conditions, not just to the large-scale density of its environment. If anything, the slow, gentle evolution in voids might remove some disruptive events that could be harmful, though that's still speculation. So the real punch isn't poetic, it's practical. A place that, on maps, looks like a giant hole in the universe can still host galaxies that, from the inside, feel broadly normal. Planets can form, stars can live long, stable lives, telescopes can be built, cosmology can be done. The sense of isolation only appears when you look out over tens or hundreds of millions of light years and count how few bright neighbors you have. On human and planetary scales, daily life would not scream you are in a supervoid. Once you accept that, the focus swings back to the early universe. If a region as extreme as the Boötes void can still look locally normal and yet be so underdense on large scales, what does that tell you about the initial conditions that seeded it? How do tiny primordial fluctuations stretched by inflation turn into a structure that is almost empty in galaxy counts and still threaded with a filament of active galaxies hundreds of millions of light years long? The Boötes void is not just a weird gap in the galaxy map, it is a fossil of how the universe started. To see why, you have to connect two very different scales: quantum fluctuations in the early universe, and a 330 million light-year underdensity that you can draw on a map today. Right after the Big Bang, the universe was hot, dense, and almost perfectly uniform. On top of that uniform background, there were tiny ripples in density, tiny regions that were slightly denser or slightly less dense than average. These came from quantum fluctuations in the early plasma, magnified to cosmic scales by inflation, that very early phase when space itself expanded extremely fast. Those tiny differences were only a fraction of a percent, but gravity had billions of years to amplify them. In that picture, a place like the Boötes void starts as one of those slightly underdense regions, not dramatically empty at the start, just a bit below average. Over time, that matters. Slightly overdense regions pull matter in and grow into filaments, walls, and clusters. Slightly underdense regions do the opposite. They expand a bit faster than the background, and matter flows out of them into the surrounding web. After billions of years, what started as a small dip in density has turned into a large, deep underdensity, a supervoid. The Boötes void is the grown-up version of one of those initial dips. That gives you a direct link between what you see now and the so-called primordial power spectrum, which is just a way of describing how strong those early fluctuations were on different spatial scales. If there is a lot of power on large scales, you will see more big structures, both big clusters and big voids. If there is less power, big structures become rarer. So when you measure the sizes and depths of supervoids like Boötes and count how many of them exist, you are feeding information back into that spectrum. You are asking, did inflation leave behind the right mix of fluctuations to make structures like this in the numbers we actually see? There's also the question of how those early fluctuations are distributed statistically. A simple inflationary model predicts that the fluctuations are Gaussian to a very good approximation. In plainer language, that means the pattern of over and under densities follows a specific, well-behaved random distribution, like heights of people in a big population. Most regions are close to average, a few are very dense or very empty, and extreme cases are rare but allowed. If instead the fluctuations were strongly non-Gaussian, the tails of the distribution would look different. You might get too many extreme overdensities or too many extreme underdensities, or not enough of them. Supervoids and superclusters are exactly where that difference shows up. They live in the tails of the distribution. The Boötes void is one of the data points that says the universe behaves mostly like a Gaussian random field, but the tails are populated by real extreme objects. You do get very big underdensities. The fact that there are only a few of them and that their sizes and counts roughly match what a Gaussian model plus ЛCDM predicts is evidence that the initial conditions were close to that simple statistical form. If observations had turned up far more Boötes-like voids, or none at all, you would be pushed toward more exotic early universe physics. Then there's dark energy, which controls how fast the universe expands at late times, and that also feeds into how voids grow. Underdense regions expand faster than average. The rate at which they puff up compared to the background depends not just on their initial deficit, but on the overall expansion history driven by dark energy. If dark energy's properties are different, the growth of voids changes. That's why people look at voids not just as empty spaces, but as dynamical objects. Measure their density profiles carefully. Map out how far their influence extends. Study how galaxies near their edges move relative to the background expansion. All of that gives you indirect information about the equation of state of dark energy. In other words, how its pressure and density are related. A supervoid like Boötes with a well-defined volume and a clear contrast to its surroundings is a sharp test case. If voids on this scale did not grow as expected, you would see mismatches between simulations and the real universe. The key point is that you are learning about the early universe and about dark energy by looking at a region where on the surface, almost nothing seems to have happened. The Boötes void is not full of spectacular mergers or giant clusters. It's a place where galaxy formation is sparse, where the main story is that matter left and didn't come back. But because it's such a clean underdensity, it's highly sensitive to the initial fluctuation level, to the statistical nature of those fluctuations, and to how the expansion of the universe accelerates over time. So when you study this huge, almost empty bubble, you are really interrogating the deepest assumptions of cosmology. You are asking if inflation produced the right kind of randomness. You are checking whether dark matter and dark energy evolve the way the ЛCDM model says they should. You are confirming or challenging the connection between tiny quantum scale ripples and 100 megaparsec scale structures. That's the shocking part in practical terms. By mapping a region where there are very few galaxies, you extract some of the strongest constraints on how the whole universe behaves. The absence of structure is just as informative as its presence. The Boötes void is not a gap in our knowledge. It's one of the sharpest tools we have for testing the story of how the universe went from an almost smooth plasma to the complex web we see now. And that loops you back to the simplest observational hook in this whole story. The fact that in what was supposed to be a nearly empty hole, an astronomer eventually found about 60 galaxies running through it in a narrow tube. If even the most extreme underdensities still host dozens of active, gas-rich galaxies, what does that do to your basic idea of empty space? And how does it change the way you think about the universe's structure on its largest scales? You go looking for nothing and you keep finding more stuff. That's the basic shock behind those 60 galaxies in the Boötes void. The story you start with is simple and dramatic. There's a huge hole in the universe, a terrifying empty region hundreds of millions of light years across with nothing inside. The data doesn't back that up. What it actually shows is more precise and in a way more disturbing. The Boötes void is brutally underdense, yes. It has something like 1/30th of the galaxies you'd expect in that volume. But it's not empty. It holds a few dozen complex, gas-rich galaxies, many of them lined up along a filament that runs through three-dimensional space. The whole is a low-density part of the same cosmic web, not a blank patch cut out of reality. Once you accept that, the role of the Boötes void in cosmology shifts. At first, it looks like an anomaly, a glitch in the pattern. You might treat it like an exception you have to apologize for. But as people map it better, it turns into a precision tool. Its sheer size and depth stress test the LCDM model. Its filament of galaxies tests how well the galaxy halo connection holds up in extreme environments. Its rarity and structure feed into constraints on the statistics of the early fluctuations and the power spectrum. Its density profiling growth probe dark energy through how voids expanded relative to the background universe. The same object that started as "this looks wrong" becomes a multi-purpose instrument for checking if your main cosmological story is actually right. The 60 galaxies you have identified so far are part of that tool, but they are not the whole thing. Every serious simulation says there should be far more dark matter halos inside a Boötes-sized void than there are bright galaxies we have detected. Many of those halos should be small, hosting faint dwarf galaxies with low surface brightness. These are exactly the kinds of older surveys struggle to find at hundreds of millions of light years. They're diffuse, their stars are few, and they barely rise above the sky background on optical images. So when you hear about 60 galaxies in the Boötes void, you should treat that as the visible fraction, not the full population. Underneath that, there is almost certainly a ghost majority of ultra-faint dwarfs, a whole population of tiny systems that current instruments either barely touch or miss entirely. As future surveys with better sensitivity and better handling of low surface brightness features start to pull those out, the raw galaxy count inside the void will go up. But remember the scale. Even if you eventually catalog hundreds or thousands of dwarfs in that volume, the overall galaxy density will still be far below the cosmic average. The underdensity is real, the detection limits make it look sharper than it truly is. That hidden population is not just a detail, it carries information about how galaxies occupy dark matter halos, especially at the small mass end. LCDM predicts a lot of low-mass halos. If we eventually find the corresponding dwarfs in voids like Boötes, the model's small-scale structure picture looks good. If we don't, even after deep searches, then something about galaxy formation and small halos or about the nature of dark matter has to give. So those unseen dwarfs or their absence will turn the Boötes void into an even sharper test over the next decades. All of this forces you to let go of a very simple link your brain wants to make. Empty equals boring. On human scales, an empty room is just that, nothing happening. On scales of hundreds of millions of light years, that logic fails. The Boötes void is empty in the statistical sense. It has far fewer galaxies per cubic megaparsec than normal, but the few galaxies that are there are busy. They have rotating disks, cold gas, star formation, active black holes, dust heating up and glowing in the infrared, gas flowing in and out. They sit on a surviving filament that itself remembers how smaller voids merged in the past. The space between them is thin, but the physics in them is not. Once you start thinking that way, the whole intuitive picture of the universe has to change. You cannot just draw a mental map with interesting regions where there are clusters and filaments and dead regions where there are voids. On large scales, even the deserts have structure. Even the most underdense bubbles are shaped by gravity, bounded by superclusters, and threaded by leftover filaments. On smaller scales, the few galaxies inside them play out all the usual processes of galaxy evolution, just with fewer external hits. The void is not the absence of story. It is a different version of the story. That is why the simple phrase, "an astronomer found 60 galaxies in the Boötes void," carries more weight than it sounds like. It is not just about clever observing or deeper exposures. It is a statement that our first dramatic label for a place was wrong in an important way. We wanted a pure whole, a clean nothing. The universe gave us a severe underdensity with a filament of active galaxies running through it. It kept the part that matters for testing cosmology, the low density over huge scales, but it refused to give us literal emptiness. So when you picture yourself standing at the edge of this great nothing looking in, what you are really looking at is the resilience of structure. Even where the large-scale density crashes, gravity still shapes filaments, gas still cools and collapses, stars still form, heavy elements still build up, and galaxies still light up the spectrum from radio to X-ray. The universe does not stop being structured just because the number of objects per unit volume drops. In the end, the Boötes void forces you into a more precise way of thinking. Empty has to mean underdense by a specific factor compared to the cosmic mean, not literally nothing there. Anomaly has to mean extreme but statistically allowed fluctuation, not violation of the rules. And remote has to stretch to cover galaxies that, on their own scales, are perfectly normal, even though on the larger map they live in one of the quietest neighborhoods the universe can make. So the next time you hear about those 60 galaxies in the Boötes void, hear the real message buried in that number. It is not that we finally filled in a blank part of the sky. It's that the universe is more structured, more layered, and more stubborn about forming galaxies than your intuition gives it credit for, even in places where, by all rights, you were expecting nothing at all. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.